Use the probe mounting stand to hold the probe carrier in place while loading a probe into the tension spring clip. Use a pair of tweezers to lift the probe from the gel surface in the package and place it into the probe carrier. Place the probe into the center of the holder channel and allow it to slide toward the back. Then slide the clip forward over the probe chip to hold it in place. Loosen the locking screw and lift the head carefully out of the dovetail mount. Place the probe carrier onto the bottom of the dimension head by aligning the pins with the holes in the carrier. The dovetail mount assembly consists of the fitting on the back of the scan head and the complementary vertical channel on the stage. Slide the head back into the dovetail mount on the stage and fasten it in place with the locking screw. Take care when placing the head in the dovetail mount. If the fixture is not aligned, you could drop the head, causing severe damage to the piezo. There are two methods for aligning the laser onto the probe. Either method can be used to position the beam. The first technique involves projecting the laser onto a surface underneath the head and probe holder to observe the beam as it moves across the cantilever. The two knobs on the top of the dimension head are used to adjust the position of the laser onto the probe cantilever. On the left side of the head, there are two knobs to adjust the reflected beam onto the photodetector. Move the stage forward to allow room for the projected laser beam. Use a sheet of paper or any suitable surface to observe the projected laser spot. Align the laser onto the probe by rotating the positioning knobs until the beam is interrupted by the cantilever arm, creating a shadow. The second method is also a convenient way to verify that the laser is in the optimum position on the probe. The reflected image of the probe is located below the focal plane of the sample and is visible as long as the sample has a reflective surface. The position of the laser spot can be viewed in this reflected image. Use the software command Move to Alignment Station in the Setup screen menu to translate the stage forward. The station is located near the back of the sample chuck. This allows the probe to be placed above a reflective surface so that the image of the laser spot and the mirror image of the cantilever can be viewed at the same time. Lower the focus to see the tip reflection image, and then move the alignment knobs until you see the laser spot visible near the end of the cantilever. As the laser moves over the cantilever arm, the sum signal should start to increase. Rotate the detector adjustment knobs to steer the reflected laser into the position-sensitive photodetector. The window on the left side of the head reveals the position of the reflected beam. Typically, the optimum position will be near the center of the window. Occasionally, the reflected beam may be too far off-center to show up in the window. It may be necessary to rotate the detector adjustment knobs all the way into their respective stopping positions and then rotate them back out one at a time until the spot reappears. The LCD screen on the stage and the software detector signal window will display the numeric value of the detector output. The intention is to balance the top versus bottom signal as well as the left versus right so that the laser is as close to the center of the detector as possible. This will result in the top, bottom, and left-right signals approaching zero. Once the position of the laser is optimized on the probe and centered on the detector, then you are ready to position the sample under the probe and initiate the approach process if you're in contact mode. If you're in tapping mode, you are ready to begin tuning the cantilever to its resonant value.
Atomic force microscopy utilizes a probe tip made from various semiconductive and ceramic materials attached to a flexible cantilever of varying length, width, and thickness. The different physical dimensions impart different stiffness properties to the probe. Contact probes such as the SNL or MLCT models have triangular-shaped cantilevers. Probes such as RESP and RESP-A have rectangular cantilevers. The most common characteristic of contact mode probes is their low range of force constants. Inside the dimension scan head, a laser reflects off the back surface of the probe cantilever and into a 4-quadrant position-sensitive photodetector. The movement of the laser across the photodetector corresponds with the movement of the cantilever as the probe bends in reaction to the sample surface forces. The lower extension of the scanner holds the piezo assembly, which consists of a tube that bends in the XY plane and a second tube that retracts or extends along the Z-axis, moving the probe holder along with it. The signal from the photodetector is processed to generate a deflection value that represents the bending of the probe cantilever. The user enters a set point value through the software interface that represents the desired amount of deflection or force on the probe. The signal from the photodetector is compared to the deflection set point, and the resulting difference is known as the error signal. The error signal is fed to a gain amplification circuit which influences the controller's response to the variation from the set point. The amplified values are then fed to the high voltage control circuitry to send the required voltage values to the scanner that will force the piezo to retract or extend to maintain the set point deflection value. As the probe encounters elevations or depressions in the sample surface, the feedback loop through the controller forces the scanner to react to the deflection change and restore the set point value. This loop is constantly being updated and maintained by the controller while the piezo is rastering the tip across the sample one line at a time. The result is a topographic map of the sample surface. Launch the Nanoscope software and select Contact Mode from the configuration menu. Align the laser onto the probe and into the detector using the shadow method or the alignment station. For a detailed explanation of the probe placement and laser alignment process, watch the separate video entitled Aligning the Laser on Dimension Icon. From the Setup interface, adjust the focus and illumination as needed to bring the probe clearly into view. Center the crosshair on the end of the probe to assure concentric tracking of the optics as the zoom factor is increased. Use the Load Probe command to select the appropriate profile for the probe you are using. Save the selection. Select the Navigate button to shift the focus down to the sample surface and open the stage position controls. Adjust the focus on the sample, zoom as much as necessary, and shift the stage to a position over the sample that is suitable for scanning. Select Check Parameters to open the Feedback and Scan Settings interface. Review parameters such as scan range, speed, and set point to assure that they are reasonable values for the probe type and experiment. If additional controls need to be invoked, select the Expanded Mode button to review parameters related to the scanner's Z-range, bias controls, and more. Once the scan parameters are satisfactory, initiate the approach by clicking the Engage command. The approach process begins by shifting the focus to the probe and lowering the Z-stage motor until the probe encounters the force region above the sample. The Z-motor slows down and the piezo begins stretching downward until the probe deflection achieves the set point value. At this point, the Z-motor stops and the feedback loop takes over the control of the piezo and probe position while monitoring and maintaining the set point value. The scanning interface opens and the scanner begins moving the piezo and probe across the XY plane of the sample. The changes in voltage that are associated with the Z-axis piezo motion are combined with the X and Y raster motion of the probe to generate a topographic height map of the sample surface. The height sensor channel displays a similar map based on position readings from the Z strain gauge sensor. Additional channels may be opened to display deflection error, which reflects the variation between the current probe deflection value and the set point value, or friction, that displays the variation in the tilt of the cantilever from left to right. While a scan is collecting, the user may choose to adjust parameters such as speed, gain, or set point if improvements in the image are necessary. Rotating the scan by 90 degrees can often reveal more features in the friction data channel. Allow the scan to complete and save the images if they are satisfactory. The results of a multi-channel contact scan can provide useful and revealing measurements. Probes used for tapping mode in air are typically shorter in length and greater in thickness than contact probes. This tends to impart a greater rigidity to the cantilever and thus a higher force constant and resonance value that is distinct and higher in frequency than probes used for contact techniques. Tapping probes such as RTESP or OTESP have rectangular cantilevers and force constants above 1 Newton per meter. The probe holder contains an embedded piezo layer under the chip mount that vibrates at a frequency generated by a signal from the controller. The vibrating piezo induces the vertical motion of the probe cantilever that ultimately results in a maximum vertical displacement, or resonance. The amplitude of the resonance is affected by the proximity of the probe to the sample surface. As the probe encounters the space near the surface, the amplitude decreases and the frequency of the cantilever can also shift up or down, depending on whether the force regime attracts or repels the probe. The set point is determined during the frequency tuning process and defines the amplitude value that the probe must achieve to successfully engage the sample. A frequency reference signal from the controller modulates the piezo element in the probe holder. The resulting waveform signal from the photodetector represents the vibrational amplitude of the cantilever. This signal is sent back into the controller. The user enters a setpoint value through the software interface that represents the desired amount of resonance amplitude. The signal from the photodetector is compared to the setpoint value, and the resulting difference is known as the error signal. The error signal is fed into a gain amplification circuit, which influences the controller's response to the variation from the setpoint. The amplified values are then fed to the high-voltage control circuitry to send the required voltage values to the scanner that will force the piezo to retract or extend to maintain the setpoint value. Once the probe engages the sample and establishes the setpoint amplitude, the scanner begins rastering across the sample surface. As the probe tip encounters topographic structures, the change in amplitude causes the scanner to respond by lifting or stretching the z-axis of the piezo assembly to restore the setpoint. By maintaining the setpoint value, the scanner creates a three-dimensional topographic map of the sample surface. Additional data can be derived from the tapping amplitude error and phase channels. Phase images are derived from the difference between the phase angle of the signal that drives the probe and the phase angle of the resulting signal from the photodetector. The shift in the phase is influenced by the forces between the sample and the resonating probe tip. Different materials can produce different amounts of phase shift. As with all modes of AFM, the procedure begins with the installation of the probe into the probe holder. Use a pair of tweezers to load a probe into the holder. Then move the spring clip over the probe chip to hold it in place. Place the holder onto the 4 pins at the end of the scan head. Take care to avoid forcing the holder onto the pins. Place the scan head back into the dovetail cradle and secure it. Align the laser onto the probe and into the detector using the shadow method or the alignment station. For a detailed explanation of the probe alignment and laser alignment process, watch the separate video entitled Aligning the Laser on Dimension Icon. Launch the Nanoscope software and select tapping mode from the configuration menu. From the setup interface, adjust the focus and illumination as needed to bring the probe clearly into view. Center the crosshair on the end of the probe to assure concentric tracking of the optics as the zoom factor is increased. Use the Load Probe command to select the appropriate profile for the probe you are using and save the selection. From the bottom of the setup interface, click the Auto-Tune button to initiate the frequency sweep process that isolates the resonance frequency and optimizes the amplitude value for the probe. Select the Navigate button to shift the focus down to the sample surface and open the stage position controls. Adjust the focus on the sample, zoom as much as necessary, and shift the stage to a position over the sample that is suitable for scanning. Select Check Parameters to open the Feedback and Scan Settings interface. Review parameters such as scan size, rate, and feedback gain values to assure that they are reasonable for the probe type and experiment. Once the scan parameters are satisfactory, initiate the approach by clicking the Engage command. The approach process begins by shifting the focus to the probe and lowering the Z-stage motor until the probe encounters the force region above the sample. The Z motor slows down and the piezo begins stretching downward until the probe achieves the amplitude set point value. At this point, the Z motor stops and the feedback loop takes over the control of the piezo and probe position, while monitoring and maintaining the set point resonance amplitude. The scanning interface opens and the scanner begins moving the piezo and the probe across the XY plane of the sample. Once the scan begins, the user may choose to open additional data channels, such as phase signals, to reveal different features on the sample surface. If a specific area of the sample is of interest, the user can activate the Zoom button to select that region. Click the Execute button to begin scanning within the newly defined area. While the scan is collecting, the user may choose to adjust parameters such as speed, gain, or set point if improvements in the image are necessary. Allow the scan to complete and save the images if they are satisfactory. The results of a multi-channel tapping scan can provide useful and revealing information. Standard tapping mode imaging involves the monitoring of a probe cantilever that is vibrating at its maximum resonance frequency. Peak force tapping involves driving the probe with the scanner's piezo at a frequency much lower than the resonance value of the cantilever. Using a nonlinear cyclic ramp, the scanner piezo moves the tip and sample together and apart within a small range of vertical amplitude. This cycle results in a force data plot over time that can be divided into approach and withdrawal segments that, when plotted as force versus Z position, will take on the familiar appearance of a force ramp plot. The system monitors the force curve to identify the point of maximum tip deflection, or peak force value, which is then utilized to control the feedback loop that drives the scanner piezo and thus the position of the probe in relation to the sample. Standard tapping mode monitors the shift in frequency or amplitude of the resonating probe and generates an image based on the response of the probe to the force gradient above the sample surface. But the data from the peak force cycle is used to maintain the optimum interaction between the tip and sample as the tip rasters across the sample surface. Peak force tapping is the feedback technique that makes Scan Assist mode possible. The result is an improvement in image quality when compared with standard tapping mode. Scan Assist probes have relatively low force constant cantilevers that are suitable for low force loads and low frequency cycling. Insert a probe into the specialized holder using a pair of tweezers and the probe mounting tool that comes with the system. Fix the probe into place using the spring clip. Place the probe carrier onto the scanner and return the scanner to the dovetail cradle. The process of using the shadow method to position the laser onto the cantilever and aligning the photodetector is described in great detail in the probe alignment procedure video. Select Scan Assist from the menu of experiment categories. Select the experiment group and then click the Load Experiment button. The software configures the system and opens the workflow toolbar. From the Setup interface, click on the Select Probe button to access the pull-down menu of probes. Select the Scan Assist probe and then save the change. From the Setup interface, perform the final alignment of the laser into the detector. Select the Navigate icon to open the head and stage positioning controls. Use the Z motor position controls to raise or lower the head if necessary to obtain a focused image of the sample. Click the Check Parameters button to display the parameters list. Typical values are shown here. Make sure that Scan Assist Auto Control is set to On before initiating the engage cycle. Select the Expanded Mode option if you want to display additional scan parameters. Initiate the Engage command and allow the probe to approach the sample and enter feedback. Monitor the trace signals from the data channels for indications of good topographic data or feedback from the sample. Undock the Force Monitor window from the control panel and adjust the data scale values as needed to observe a sufficient range of the force plots. The user has the option of turning the Scan Assist Auto Control off and selecting individual control over parameters such as set point or gain. Adjusting the gain value can affect the noise level of the image. Adjusting the set point can increase or decrease the force load cycle on the sample. Manual tuning of the individual scan controls is entirely optional and may improve the image quality, but if adjustments are providing no significant improvement, then it may be preferable to leave the auto control on and let the software adjust the values while the probe is scanning. If your software configuration is displaying the set point value in volts and you prefer to use force units, then open the Tools pull-down menu and select Options. The pop-up side menu displays an option labeled Classic Gain and Set Point Mode. If this option is checked, click on it to deselect the option and then open the Setup interface again and select the Scan Assist probe once more. Afterwards, open the Parameters interface and the set point should display in force units. Once the scanning parameters are optimized to your satisfaction, collect the scan data from each relevant channel to produce the final images. With a minimum amount of interaction from the user, the Scan Assist controls can produce clean, relatively noise-free images from a variety of samples, such as the examples shown here. Initializing the Nanoscope or NanoDrive software from the AFM workstation will simultaneously launch the Nanoscope Analysis program, which runs in the background. Images can be processed on the instrument computer or transferred to a separate computer for analysis at a later time while the instrument is offline. Nanoscope Analysis comes in a 32-bit and 64-bit version, and it can be run under Windows XP or Windows 7. When the interface opens, the user can define the workspace area for one image or two using the span and unspan commands. The Browse Files tab expands to provide a thumbnail view of each file from a selected folder and allows the user to select and open that file. Each nanoscope file can contain multiple data formats. Additional files can be opened in the same pane or in a second pane for side-by-side comparison. Some image files may require flattening operations to remove scan artifacts that cause variations in the data from line to line or across the entire field. This is often useful before making measurements across regions or multiple lines in the topographic map. The History tab provides the user with an option to go back and forth through a series of processing steps to view the changes. The undo command also reverses the action previously taken to a point that the user may prefer to keep before making different choices. Once operations have taken place, the user may save the displayed images and the processing steps for later use by selecting the Save Workspace command and naming the workspace file. Recalling the file restores the work area and the history of all the processing steps previously taken. Sometimes it may be necessary to process numerous image files using a set of sequential operations with multiple steps or repetitive commands. The user can perform a sequence of processing steps on a typical file, and the steps will be recorded in the history cache, as shown here. Opening the Auto Program dialog window reveals the recorded commands from the history cache. The sequence can be saved to a file name and then opened again, restoring the command steps into the Auto Program window. Clicking the Add button allows the user to select a new file or set of files to be processed through the program sequence. Select a directory location for the results to be filed, along with any desired reporting options. Then click the Run button to execute the operation sequence on the selected files. The resulting report files can be opened to view the tabulated calculations. After leveling the image, we can generate statistical topographic data using the roughness command, which provides multiple expressions of the pixel height averaged across the entire image or within defined areas. The user can also selectively exclude areas of the image to eliminate anomalous features. Images that have distinct boundaries between regions or structures can be subjected to statistical processing via the particle analysis command. The user can select features above or below a point in the depth histogram and move the cursor to select the threshold limit that defines the features of interest. The Modify tab allows the user to alter the selected feature dimensions. The Select tab limits the selection to features within the image boundaries or to count specific features. Force curve files can be opened for offline review or processing. The baseline correction operation can adjust the original measurement offset or tilt. Use the movable cursors to select the desired section of the curve for correction, choose the data plot options, and then execute the operation to force the curve to the zero reference value. Use the line plot display to measure the sensitivity of the deflection axis. Move the cursors to mark the boundaries of the linear portion of the ramp and select the fit model. To measure the adhesion force, set the active curve to retract, zoom in on the pull-away point if necessary, and move the cursors to either side of the pull-away point. The difference between the y-axis values reflects the adhesion force between the sample and the probe tip. The user has the option of changing the displayed plot units to reflect the force or deflection distance. Data points from a force curve can be saved to an ASCII text file via the export command, which is available from a pop-up menu when the user right-clicks on the curve display. Opening the file reveals the file header information along with the force and z distance points separated into columns. Force volume image files can be opened in nanoscope analysis to display deflection or adhesion data according to the user's requirements. Use the cursor to select various locations in the image to display measurement data from that point. The offline parameters list allows the user to select between separation or deflection display modes, to align the display curves to a common reference point, and to enter values for deflection sensitivity, spring constant, or other parameters as required by the modulus model being used. The user may also decide to include or exclude adhesion data or to limit the display to the extension or retraction portion of each curve, as well as changing the minimum and maximum boundaries of the force curves. Display options include selecting data from single points in the image, or to overlay multiple points for comparison, or to display curves from multiple points within a defined region. To export force data to an individual file, use the Save Curve button to select the destination. To gain more in-depth knowledge about the analysis software, use the Help command from the pull-down menu bar to open the online user manual, which contains explanations of each command and operation in the program.